So, good afternoon, everyone. After the wonderful inauguration session, I would like to invite you all in our first session of 5th International Conference of International Conference on Science and Engineering of Materials. Myself, Dr. Babita Tripathi and Dr. Shalu from Department of Physics, School of Basic Sciences and Research. It is my privilege to introduce the session chair, Professor Carol, a distinguished scientist from the Institute of Physics at Nicolaus Copernicus University. With an impressive career spanning several years, he has made significant contributions to the field of mixed crystals, crystal growth techniques, and photothermal investigations. His expertise also extends to cutting-edge research on solar cells, DSSC, supercapacitor, and spectroscopy techniques. He is the author of over 80 high-impact journal articles and active participant in international collaboration with scientists from France, India, Romania, Taiwan, and many more. We are honored to invite him to chair a session for the first session of the conference. So I would like to welcome our session chair, Professor Kalor. Welcome, sir. Please come on, guys.
Okay, thank you. Welcome, everybody, for the first session. Today, we will start with plenary talk, which will be given. Okay. Yes, which will be given by Professor Maria Manuela Silva Pires de Silva from Portuguese. Professor Maria is a renowned associate professor at the University of Minho, Portugal. Her groundbreaking research spans polymer electrolytes, sustainable energy materials, and solid-state electrochemical devices. She has authored over 215 peer-reviewed articles, contributed to numerous book chapters, and has an impressive H-index of 40, reflecting her substantial impact in the scientific community. Professor Silva is recognized for her innovative approach to using natural polymers for eco-friendly applications and her leadership in international collaborations, including projects under Horizon Europe and other global initiatives. Her work has garnered prestige awards, including journal cover recognitions and distinctions at international conferences. With decades of experience in both academia and research, Professor Silva's contributions continue to drive advancement in energy storage and smart material technologies. Please join me in welcoming her to share her invaluable insights. So please, the floor is yours.
This is the laser pointer. From there you can point the laser.
And for moving,
Yes, this
yes.
is
Okay.
moving up.
Okay.
This is back.
Okay.
Right?
Okay.
Okay, what do you want?
Okay. Thank you very much.
Need extra water or anything, you can ask.
Okay, thank you. One more time, good morning, all of you, and thanks for the introduction. I'm come from Portugal, as I tell you in the. Oops. Okay. And my presentation, I will show some kinds of my work, a brief introduction and motivation for my study, preparation of materials very briefly, and then I will show you 2 examples of my research work, some conclusions of each work, and acknowledge. As you know, at this moment, the energy is mainly consumed by three sectors: building, industry, and transportation. The building sectors represent 13 to 14% of primary energy in the world. In Europe, we spend this kind of energy for heating, cooling, and lighting in our life. And of course, for transportations, we make some lithium-ion batteries, and these kind of devices have emerged as a foundation of modern energy storage systems. The continuous questions for safer, more efficient, and environmental sustainable energy storage solutions. And I make some technological applications and use solid polymer electrolytes. I think and I believe this is a solution or some solution for the climate transition. The objective in the present is the full decarbonization of the cities. And for example, we have to see what happened to raw materials, to make advanced materials for cells, for models, for packs, for applications, and of course, end of lives. We have to recycling the materials and use it in other devices. Is an example, of course. I would like to speak a little bit about battery generations. In this table, you can see some battery generation, and my research is in generation 4. Of course, I make some work in generation 5. For example, sodium batteries is generation 5. But as I tell you, my focus in generation 4. In generation 4, we can divide it in generation 4A, because we use solid state with conventional materials. And in this kind of batteries, we development low directly current resistant active materials. We have to reducing thickness of the anode. We development thin solid electrolytes, and of course we need higher ionic conductivity. We development concept strategies for manufacturing new solid electrolytes interlayers. I will show one example of my work. We have to improve interface design to ensure the efficient charge-discharge and electrochemical stability, and improve cell mechanical stability. And we have to propose approach to expect it to have no negative impact on energy density, safety, and cyclability. Of course, we have to development new current collectors. Generation 4B, we use solid state with lithium metal-based anode materials. And here, new materials and new chemistries to increase the energy density beyond the state-of-the-art of batteries used in electromobility applications. At the anode side, lithium metal appears as the most appealing choice for generation 4B, solid state with lithium metal-based anode materials. We have to improve reversibility, homogeneity, and density of electrodeposition process by doping and coating strategies. We have to take solutions for manufacturing and handling lithium metal shipped in dry atmosphere. We have to have new solutions for low cost. It's very important to make batteries with low cost to make, for example, electric cars with a more cheap cars. Another technology we can thinking is anode-less. Is very outstanding technology, could also be developed by design current collectors for reversible electrodeposition of lithium. Solid-state electrolytes and lithium metal anodes open a new cathodes chemistry reaching higher energy density, such as lithium-free cathodes. Okay? And we have to improve interface design. Also, of course, we need to study the interface. Is very hard work, but we can learn what happened about in the interface and improve the cycle of batteries. But as I tell you, it's not easy to see what happened in the interface, especially in operando conditions. Also, we need, for batteries, development, sustainable and safety non-lithium battery solutions with no critical raw materials. It's very important. We need to sustainably and compatibly with supply chain, and we have to manage the toxicity and safety risks. And as I tell you, we have to make batteries with low cost. Another things that I'm doing in my research is electrochromic devices. Why I study electrochromic devices and batteries? Because we can use solid electrolytes, but solid electrolytes sometimes not have so higher conductivity that I need for batteries. And then I think we can apply, for example, in electrochromic devices. We need conductivity, but not so big like to need for batteries. And if you think, for example, in an ideal smart Windows, when we can use electrochromic devices, here in this schematic diagram, you can see an ideal smart windows. Then can, for example, in harm days, the infrared radiations can be reflected and not go inside the building. And in the cold days, we need to the infrared reaction, and we can, in ideal, to maintain the temperature inside the building. It is, of course, ideal, okay? The smart electrochromic devices is not so different from batteries. It's like more or less a sandwich, okay, with different layers. We can use glass and different electrodes like indium tin oxide, and we can use electrochromic coating tungsten oxide. But when we use polymer electrolytes, we can use, we can change, for example, the glass with the plastic, okay? Why I use polymer electrolytes? Polymer electrolytes is a solvent-free system with ionic conductivity phase, and we can dissolve in polymer gas salts. What advantages of solid polymer electrolytes? The chemical, mechanical, and electrochemical properties of solid polymer electrolytes maximize the possibility of their application in a broad variety of electrochemical devices. Solid polymer electrolytes can play three functions. Ionic conductors, they can be a good separator and adhesive. And in order to achieve a successful application, solid polymer electrolytes should satisfy another three requirements: performance, durability, and cost. The performance is defined by the ionic conductivity of the materials, which should be as higher as possible, special for batteries, as I tell you. The electrochemical stability windows, which is especially important for energy storage devices, and specificity, for example, for sensors. I have some works in sensors, not so big works, but some works. And the durability of the devices will be as long as the capacity of the solid polymer electrolytes. And lastly, the cost of devices should be enabled to commercialization. But of course, we use some materials with limited abundance, like lithium and palladium, and we have to sometimes to change these critical materials or use small quantities of lithium as possible. In my work, I use some synthetical materials, synthetical polymers, but at this time, I try to use natural polymers. Of course, we need to use sustainably and friendly environmental materials to do these devices. Why I use natural polymers? Because they are renewable, biocompatible, biodegradable, and sometimes we have biopolymers with low cost. I use many of the natural polymers. Some of them are not so traditional, like, for example, silk. We normally think silk for clothes, but we have some properties. We can use this kind of polymers in electrochemical devices. Of course, I use others, for example, chitosan, cellulose, is more traditional natural polymers. I have, for example, this work with silk for batteries. If we are interested, you can see this paper. It's a very nice paper with silk for separators for lithium batteries. Normally, the natural polymers don't have so higher conductivity if we compare to more synthetical polymers, but as you can see in this table, with different polymers, we have conductivity at ambient temperature. They are satisfied for application in batteries. Okay? What about the preparation of materials? I only show you very briefly the preparation of materials. You can find it in my papers, but one thing that I would like to tell, we need to have very easy preparation if you wanted to put these materials in industry. If you have synthetical or preparations are very difficult and with different and expensive materials, I think it's not possible to put it in industry. I used solvent casting methods and sol gel methodology. Sol gel methodology is more difficult, in my opinion, to translate it to the industry. And one of the examples that I would like to show you is for lithium-ion batteries with collagen and chitosan hybrid membranes. And here you can see the compositions of dry membranes. We have to change the percentage in the collagen and chitosan, and we use the freezing drying methods for preparation the membranes. In scanning electron microscopy, of course, I only show you some characterization techniques. I have many others, but I don't have time to show all of characterization. But the morphology of the membranes is an essential characteristic to consider in battery separators, particularly in relation to pore microstructure and connectivity. Here in the table 4, you can see the porosity values of the different membranes. It's a good performance for batteries. And ionic, in this table, you can see the ionic conductivity and lithium transference number for the collagen ketosane membranes at room temperature. And as you can see, they have a good conductivity and a transference number value. And here you can see the charge-discharge battery behavior exhibit with an increase in C rate, a decrease in capacity is evidence attributed to ohmic polarization. And here also you can see the obtained discharge capacity value for different rates. To compare the charge-discharge profile between the membranes, in this figure we can illustrate the corresponding profile curves at 3-5 rate. The discharge capacity for the different membranes you can see as decrease, of course, with different membranes. In this figure, you can see the rate performance of all membranes, the discharge capacity as a function of cycle number. All membranes showed good cycle stability through the cycle number. It is observed that the 7-ketosano membranes exhibit the most favorable charge-discharge capacity, even a higher C rate. Furthermore, a close correspondence is noted between the discharge and charge value for all C rate, suggesting minimal charge lost during the process and so indicating a Coulomb efficient of 100%. Additional, the consistent results across different charging rates highlight the reproducibility and stability of the system. The conclusion for this study, taking into consideration the circular economy and sustainability issue for the development of added value products through the use of host materials in this work, sustainable membranes based on collagen and ketosane polymers were developed. Pore morphology with connected pores and porosity above 900% is obtained where the pore size is affected by the ketosane content. The use of ketosane increased mechanical and thermal stability compared to the poor collagen-based membranes, and the best member for the C and 2C rates is this one, due to its ionic conductivity values was present. The other example that I will show you is for electrochromic devices to use in smart windows. And we prepared the diuresyls hybrid electrolytes doped with proton ionic liquid. And as you see in this figure, we have transparent membranes and we can use it in electrochromic devices. Here we have some techniques to characterize the membranes and, for example, X-ray for these kind of hormolites exhibit a prominent broad Gaussian sharp bands attributed to ordering with the silicium domains. In the DSC curves, the endotherm peaks detected at 21 and 35 for the concentration of 14 and 40 degrees are associated with the fusion of polyethylene oxide chain. A very broad endotherm around 100 degrees detected in the case of the samples, some samples, is probably due to the realized extra solvents, for example, water or ethanol. The ionic conductivity of ionic liquids doped polymer electrolytes depended on the ionic liquid concentrations, on the ionic charge, on the conductivity of pure ionic liquids, on the viscosity, and on the type of host polymer. The increase of proton ionic liquid concentration leads to an improvement of ionic conductivity normally. Sometimes it's not so like this. All the samples reveal a no linear variations of ionic conductivity with temperature, which is typical behavior of disordered electrolytes, well described by the Vogel VTF equations. And these kind of materials are applied, as I tell you, in electrochromic devices, smart windows, and here you can, when you change the voltage, you can have different colorations and, for example, bridge hot, we can use 0.0 volt. For SPI bright harm, we use minus 2.0 volts, or dark cold, we use minus 2.5 volts. With the good transmittance all of these operations modes. In this state, you can see some conclusions about this system, and with this system, we have higher Schwitt efficiency, higher optical density modulations, higher optical contrast region in the visible regions, and of course we can use this system in infrared region also, and we have excellent coloration efficiency. And now I would like to acknowledge my university for the facilities of Center of Chemistry and some of projects that I have to finance my work. And of course, I would like to Professor Parnam, and thank you for your attentions.
So thank you very much for perfect timing and excellent presentation. Thanks again. And maybe there's some time for questions and some comments. Okay.
Thank you. Thank you so much, Professor Silva, for a very interesting talk. This is Dharmendra Singh from Yulco, France. So obviously, the concept of a smart window is a new concept. You showed that the minimum operating voltage that was required to operate this smart window, that was between 0 to 2.5 volts, something like that. So, but I think it also depends on the size or area of the smart window. So is this operating voltage is optimized for what area of the smart window?
It depends the system. Some of them we have like 5 million cycles to colorated and blended stage. It's very hard because we need to make many cycles because we need to have a smart windows. It longs time to put in our house, for example, of course. But I think I don't, if you change, for example, to use it in infrared radiation, it's more complicated. Because, for example, we can use lanthanide ions and make some concentrated to catch the solar energy and not needed to use energy, other energy, to put this in operation. But I think this technology is not possible at this moment to transportation to the industry. But if we can use a simple system to only change color to harm, I think it's possible. I have some companies in Portugal. They are interested in to put this in industry.
Okay, there are any more questions, comments? I wonder what would be the cost of such smart windows?
The cost?
Cost, yes, the cost.
At this moment is not so small cost.
Yeah, I understand, but how you think that it will be possible to lower the cost
yes,
of mass
yes.
production and so on?
Yes, yes. If we can use natural polymers, we can lower the cost, and I think it's possible to have this technology in few years.
Okay, nice.
Yes,
very nice.
because we have smart windows, but with liquid electrolytes. But if we wanted, for example, to use it in harm countries, like Arabia Saudita, Malaysia, India, of course, we need a solid electrolyte.
Yes, of course.
They can use in more times.
Yep. Okay. Okay. Thank you very much. Thanks the speaker again. The next speaker is Dr. Monika Michalska from Czech Republic. She will give the talk about the surface modification with metallic NPs on the materials used as supercapacitor electrolytes. And let me introduce Dr. Monika Michalska is distinguished researcher at the crossroads of material science, chemistry, and nanotechnology. She earned her PhD in 2016 from the Institute of Electronic Materials Technology in Poland, Warsaw. Following her doctoral studies, she expanded her expertise through scientific internship in Taiwan, the Czech Republic, and Poland. Since 2020, Dr. Michalska has been a researcher at the Technical University of Ostrava, Czech Republic. Prior to this, she served as an assistant professor at ITME, showcasing her dedication to advancing knowledge through both research and teaching. Her work focuses on the synthesis and physico-chemical characterization of nanomaterials, particularly for secondary batteries and supercapacitors. She is also adept in surface modification techniques involving ceramics oxides, metallic and carbon coatings. Additionally, her research contributes to developing materials for applications in photocatalytic wastewater treatment and photoluminescence. So please, Monika, the floor is yours.
Okay, thank you very much for my presentation.
Oh, you have the pointer.
Pointer.
Is this the correct presentation? Is this the correct presentation?
When is? Yeah, it should be. Okay. So I'll come here. Good afternoon, ladies and gentlemen. I would like firstly to thank conference organizers for giving me an opportunity to be here and present my work. Especially I would like to thank Professor Pramod, because for me it's like for the first time to be in India. And I would like also thank Dr. Amrita Jain, my dear friend, also for supporting me here. And I would like to present, okay, my work. So within the beginning, I would like to show you that I come from the Czech Republic. So when we look on the map, worldwide map, you see that the Czech Republic is in the middle of the Europe. When we look on the map on the Europe, we see that the Czech Republic is in the European Union. What is more important about the Czech Republic? Czech Republic is also called like a Czechia or Bohemia. Let's say the country is not so big. You can see also on the map, and we have about 11 million of people as of 2024. What is also important from the Czech Republic, that the capital of the Czech Republic is Prague. Okay, you can see the map. So Czech Republic is near the Germany, Austria, Poland, and Slovakia. And I am coming from the VSB Technical University of Ostrava, and this city is near the Polish border. It's about 15 kilometers to Poland. So what is most important from Ostrava, you could see my photo. So basically the inhabitants, it's about 218,000. We have also, Ostrava is the third largest city in the Czech Republic, the second largest in the region of Moravia, and the largest city in the historical land of Czech Silesia. Ostrava was very famous in 18th and 19th years with the production of steel. So here you can see my photo within the visit some kind of the company which was creating a steel. Some beautiful old town in Ostrava and very famous river. Okay, about my university. So my university was established 165 years ago, and it's kind of the university which has in total 7 faculties. On the picture you can see that 2 years ago, Amrita, it was, yeah, when you visited me here. So I am representing the Faculty of Materials Science and Technology, and basically the faculty is trying to connect industry with science. And within the faculty, we have in total 7 departments, and I am representing the Department of Chemistry and Physico-Chemical Processes. We have a long-term collaboration within the national and international universities. About my presentation, I was thinking to show you something about surface modification of carbon materials, then transition metal oxides, and some final remarks. But what is more important about the materials? Here you can see some kind of the list of materials which are dedicated for cathode and anode materials. For example, for lithium-ion batteries, we could use them for sodium batteries or for SL electrodes of supercapacitors. What is, let's say, most important? We are mainly focusing on transition metal oxides. So within my story, within PhD thesis, I was dealing with the materials like transition metal oxides doped with lithium ions, and the thesis was mainly focused on lithium manganese oxide, which was used as a cathode material. So here you can see some main information about that material. So what was important, that the high working potential for this material was 4.1 volts versus lithium. Of course, low cost of raw materials, low toxicity, and high safety. So first proposition was to synthesize this material within the modified Solger method. So I proposed this method and try to analyze the effect of the complexing agent on the structural, morphological, and finally electrochemical performances. And for the complexing agents, we use citric acid or citric acid with combination like with acetic acid, ethylene glycol, and glycolic acid. When we analyzed the crystalline size and the morphology, we could see that when there was used some kind of the combination of the complexing agents, the average particle size were less in comparison to the when pristine material was synthesized with only citric acid. What was important for us, it was to test this material in lithium-ion cells, where the cathode material was lithium manganese oxide and anode was lithium metallic, and standard electrolyte like lithium hexafluorophosphate with SEDMC in composition 1:1. So here you can see the high-rate tests which were performed for all 4 samples, and the summarization of the results in the table. What was important to note that within the percentage of initial capacity after 100 cycles, each material possessed more than 90%. And when we try to find the best material, so the best 2 materials were synthesized within the composition like citric acid with acetic acid and citric acid with glycolic acid. Next, there was the question, okay, what could happen if we modify the pristine material like lithium manganese oxide with cerium dioxide? And here you can see the flowchart of the modification, of the surface modification which I proposed and deposition of cerium oxide particles. What was important for us when we look on the structural analysis, we saw that the pristine materials was connected within the cerium oxide, and Finally, when we performed the electrochemical performances, we achieved very interesting results because the modification only within 1% of cerium oxide gave us the positive effect within a specific discharge capacity within various C rates, and of course, percentage of initial capacity after 100 cycles. Another my work, it was also connected within the Polish-Taiwanese project because I am, let's say, from Poland, but moved to Czech Republic as it was mentioned about me. So there was another question, what could happen if it is possible to substitute manganese ions with cerium ions into the lithium manganese oxide structure. Okay, so I proposed the modified Sauger method, as you can see on the flowchart. And what was important in this work, I analyzed the effect of the heating process. So there was, let's say, two propositions. One, when material was firstly heated in nitrogen and then in air, or only in air. Why? We have an answer here. So basically, on the surface, on the lithium manganese oxide, we saw that the cerium oxide is deposited, but we know from the structural analysis that also some ions were also substituted manganese ions. Within the morphology, it's completely different than I showed you before. So, and the average particle size for the cerium dioxide were about 10 nanometers. What was also important to know that the substitution of the cerium ions into the lithium manganese oxide structure was between 0.01 to 0.03 mole. So it was very, very small amount of ions which were used for the doping. And we performed the high rate test for this kind of the materials which were which were synthesized in different 2 atmospheres. What I also like to do is the comparison of the results in the table. So here you can see the comparison of the materials which were only heated in air marked with A, and within 2 atmospheres in nitrogen and then in air labeled as BA. So within the table, when we compare the pristine material, lithium manganese oxide, and the material which was doped only within 0.01 mole, we see very good effect within the specific discharge capacity and also the percentage of initial capacity after 150 cycles. What was also important to analyze for this kind of the materials, so it was also capacity loss per 1 cycle. So we could see that the capacity loss per 1 cycle was smaller for the materials which were synthesized within 2 atmospheres. Next material, which I was working with in my PhD thesis, it was lithium titanium oxide, which possess theoretical capacity of 175 mAh per gram. The operating voltage is high because it's 1,5 volts versus lithium. This material is also called like a zero-strain electrode due to the charging and discharging processes. The capacity loss is very, very small, and of course we don't see the effect within the structural changes. Of course, it was kind of the advantages, but disadvantages of this material is low electronic and ionic conductivity. But like a chemist, we are here to try to modify this material. Also, the selection of this material was to build a lithium-ion cell, where the cathode material was lithium manganese oxide, anode material was lithium titanium oxide, and finally the working voltage was between 2 to 2.5 volts. Okay, so first method which I proposed, it was the solid-state synthesis, and within this method I analyzed the effect of milling time on the structural, morphological, and electrochemical properties. And what is important to know, that the material each time which was synthesized was pristine. Within the prolonged time, the average crystallite size were almost the same, as well as the particle size when we look on the scanning electron microscope. But as an electrochemist, there was the question how the material work. So we performed the high-rate test, and you can see that the best material after 25 cycles within different C rates was the material which was synthesized within 30 hours. But when we summarize the results in the table, you can see that the economic process was the synthesizing material within 24 hours. Okay. Here I would like to show you another proposition of the synthesis of lithium titanium oxide pristine material. This material I synthesized within a three-step solid-state synthesis. What was important to tell you that after achieving the pristine material, I proposed the low-cost chemical synthesis for the deposition of silver nanoparticles, and the amount of the silver nanoparticles was between 1 to 5 weight%. And you can see on TEM images that the silver nanoparticles were about 5 nanometers, and they were homogeneously deposited. We were also able to find the silver nanoparticles on scanning electron microscopes. And finally, when we performed the electrochemical measurements, here you can see the high-rate tests. After 25 cycles, we see that each modification within the silver nanoparticles of the pristine material give a positive effect on the electrochemical performances. And when we summarize the results in the table, we find that the best material was lithium titanium oxide, which was surface modified within 3 weight% of silver nanoparticles. Okay, here it's something different, some kind of the modification of lithium titanium oxide with titanium dioxide, and creation some kind of the mesoporous, microporous material. The material I synthesized in Taiwan, and you can see that the rutile form of titanium oxide was deposited homogeneously on lithium titanium oxide surface. And then we performed some cyclic ability tests, and finally we could say that this kind of the proposition of the material and modification gave us the positive electrochemical results. Okay, so back to my presentation, because it was kind of the history about this, what I am doing, I was doing, and I am continuing. So about the supercapacitors. So we know that the supercapacitors are, let's say, very important and having kind of the attention of researchers owing to possessing some high power density, rapid charging, discharging processes, and robust cyclability. And we know that there are a lot of application of supercapacitors, and also we know that they are very good connected within the buffers, especially lithium-ion buffers. So basically, according to the charge storage mechanism, we could say that we classify the supercapacitors within the electric double layer capacitors and the pseudocapacitors. Within the first, we know that it's important that we use the carbon materials. With the second one, we could use like transition metal oxides or some kind of the conductive polymers. Of course, we cannot forget about the supercapacitors like hybrid capacitors, where we have some kind of the symmetric electrodes. For asymmetric electrodes, first, let's say one material could be a carbon one, so it's like from ADLC, and second could be from pseudocapacitors. And this work we are realizing together within Dr. Amrita Jain. So first, I would like to show you the method of the modification of activated carbon material, commercial one, within the silver nanoparticles. And it should be noted here that this is the low-cost method, environmental friendly. And for the chemists, we know that we are also not using some reducing agents, so it's also important. Within the structural analysis which we performed, because the material was modified within 1, 3, and 5 weight% of silver nanoparticles, we firstly performed the structural analysis, and we were able to observe the diffraction lines from the carbon material, which was activated carbon, and also the diffraction lines which are characteristic for metallic silver. Then we performed the Raman spectroscopy analysis, which showed us classical spectra for the carbon material like D, G, 2D, and D plus G. And here you can see the assignment for this band. We also would like to know how the morphology of this material look like. So basically, we know that the silver nanoparticles were less than 10 nanometers, and the silver particles were deposited on the surface as well as between the nanosheet layers of carbon material. How we performed the electrochemical analysis. So here you can see some proposition which with Dr. Amrita we analyzed, and the gel electrolyte was used. So basically it was like a symmetrical configuration. We had a chance to perform some standard electrochemical analysis, and mainly I would like to focus here and show you that the proposition of the modification of activated carbon within the silver nanoparticles give us a positive effect within the specific capacitance, energy density, and power density. What was important that the material, which was surface modified with 3 weight% of silver nanoparticles, possessed the best electrochemical performances, which you can see in the table. And it is also comparison within the material, like, for example, lithium titanium oxide, which was modified with silver, which I showed you before. So it's enough to modify the material. And some kind of the highlights from our work. Another our collaborative work was the modification of activated carbon with copper nanoparticles, and the deposition of the copper was only one weight percentage. And we tested this material in a supercapacitor and water purification and achieved very interesting results. We performed some transition electron microscope analysis, and it was, let's say, very difficult to find the copper particles on the activated carbon. But finally, we could say that the presence of copper atoms we found, which could exist as a kind of the clusters. And the particles were lower than 1 nanometer. For this material, we performed some structural and morphological analysis, and we were able to observe within the morphology that the material is completely different that I show you. When we modify the material with silver nanoparticles, it is much more dense, and we could say that it's amorphous. Within the structural analysis, we observed the deflection lines for carbon, standard for carbon material, and similar like for Raman spectroscopy analysis. We performed some electrochemical tests, and this what is important to note, that within the modification of material within 1 weight percent content of copper, we achieved very interesting results, and the capacity was higher in comparison to the pristine material. And you can see the comparison of the results in the table. Yeah. Okay. Another modification within the carbon material, which we used for electrode in supercapacitor, it was multi-wallet carbon nanotubes. And once again, I proposed the modified method, which was, let's say, low temperature chemical approach without using a reducing agent for the deposition of the silver nanoparticles. And here you can see the flow chart, how the deposition was done. So here you can see the XRD patterns for the pristine material like multi-wallet carbon nanotubes, and within deposition of the silver nanoparticles on the surface of multi-wallet carbon nanotubes. And we had a chance to predict that we observed the silver particles within the XRD analysis. When we performed the TEM analysis, we detect the presence of silver nanoparticles, and they were about between 5 to 10 nanometers. Finally, we performed some electrochemical tests, and what is important to know that within the modification of the material within silver nanoparticles in comparison to the pristine material, we achieve better results. And what, of course, we could say that the silver particles were uniformly deposited on the surface on the multi-wallet carbon nanotubes, what, let's say, resulting in the formation of the efficient transfer of crosslinks for the electrons, and charge transfer mechanism was also improved in the supercapacitor cell, what, let's say, give us a favorable impact on the electrochemical performances. And finally, surface modification of the materials like transition metal oxides with metallic nanoparticles. So here you can see the flow chart of the synthesis and deposition of silver nanoparticles in the weight amount between 1 to 5 weight percent. The material like transition metal oxide was commercial one cobalt oxide, but within the XRD analysis, we were able to detect that the material was kind of the composite between two cobalt oxide materials. So here you can see the XRD pattern and scanning electron transmission microscope images. And finally, to summarize this kind of the work, because also this work, in this work we also proposed, let's say, a completely new electrolyte. So we could say that the metallic nanoparticles or silver, which were deposited, were between 1 to 5 nanometers. And it was completely different situation for this material that the electrochemical performances we achieved when the material was modified with highest amount of silver nanoparticles. And final remarks for the modification of the carbon material within silver nanoparticles. So I show you the modification, the surface modification with silver and copper nanoparticles of the activated carbon and multi-wallet carbon nanotube. This is what I mentioned to you, that the process was very simple, cost-effective, and environmentally friendly. We achieved also very good electrochemical performances when the material was modified within silver or copper. And final remarks from the transition metal oxides are almost the same. Here are publications where we published our results together. And thank you very much for your kind attention, and I'm looking forward to collaborating with you. Thank you very much.
Thank you, Monika. There is time for comments and questions. There is another microphone there or not? Okay, I'm going.
Hello, ma'am. Good afternoon. So I have few queries. You spoke about EDLCs. So you modified using certain nanoparticles and you said that there is an improvement in the capacitance. I would like to know what was the changes in the surface, like pore size, surface area, and how did that impact, like surface modification, how did that impact the performance? Because you know that pore size, pore volume, and surface area is also very important for these performances. So how do you what do you say about that?
Of course. So to answer you, thanks to the modification of this kind of the material, we also observe that the surface area increased, and also within the pores also increased, what also affect for the electrochemical performances.
And did you prepare the activated carbon or procured it and then modified it? Like what was the typical surface area for activated carbon, whatever you have used? Because the commercial available are usually around 1,600 meters per gram or 1,800. So after that, what kind of changes did you observe, like in surface area? Like what did happen? Like Did it increase or?
Yeah, definitely increased. The area increased, and it was very interesting because, let's say, when we evaluate some data, it also depends of the method how you propose. So within our proposition of the deposition of the nanoparticles like silver or copper, we observed that the surface area was higher for the modified material than pristine one.
And don't you think that the probe sonication method would be better than the water bath? Because water bath, I saw that the sonification was done by a bath sonicator. Don't you think that probe sonicator will be work better for proper dispersion?
Yes, definitely yes. And thanks to this, we achieved the fine particles, and they were uniformly distributed.
How stable they were, like how long they were, because I've seen that whenever I tried for dispersion, they do not disperse properly. That is when probe sonicator comes into picture, and they properly disperse for a long period of time. So that is what I was asking, because when I tried with bath sonicator, they do not work well in dispersing these nanoparticles.
It was kind of my previous work, yeah, when I show you a lithium titanium oxide, yeah. So that's why I proposed that here we could try also modify the material and use some kind of the sonication process, yeah. And of course, it depends of the pristine material, how it's prepared. What is the morphology of the pristine material? Because, for example, when I show you the morphology of the activated carbon with copper, so it was completely different morphology. As I also mentioned, that the material was dense and amorphous. But, for example, within the silver nanoparticles, we were able to detect the spheres of the silver. Yeah. So this is, let's say, kind of the method low cost, yeah, without reducing agent, which I'm, let's say, trying to utilize for the materials, not only, for example, for bufferers, supercapacitors, but we are also tested the materials within the photovoltaics and in photocatalysis as well.
One more question, ma'am. You tried the cyclic voltammetry from 0 to 1 volts. Did you try for higher voltages, like wide voltage windows?
For this kind of the material and electrolyte, we were able only to use this kind of the potential.
You didn't try for high voltages?
No.
Thank you.
Okay, let's give the chance for more. So another questions? There are some. Okay.
Thank you for a very nice talk. So as I have seen that you have utilized the silver and you said that you have modified this activated carbon surface with the AG. So when you deal with this type of system, the first concern is the oxidation of the silver nanoparticles. And second thing, I would like to your comment on that how you stabilize the system, because when you use these systems in the ambient condition, obviously the performance of the supercapacitor or the photovoltaic system or whatsoever will not show the same performance. And the second thing, I would like to know that how you did the surface modification or surface functionalization, how these silver nanoparticles are being attached with your activated carbon or with your multi-wall carbon nanotubes.
Okay. So within the first question, it was about the deposition, right? Because let's say I forgot your question.
Okay, first question was like how you deal with the system, because when you have AG incorporation of AG silver nanoparticle in the system, they will be oxidized during the measurement or after some cycles. So how your system was stabilized after maybe 50 cycles, 100 cycles or so on?
So let's say we were not doing this kind of the analysis, but we know that the deposition of the silver was in metallic form. within the XRD analysis or TEM analysis. So this is something what is important to note.
Okay, and how you modified the surface of your carbon nano MWCNT or activated carbon with silver? So how these silver nanoparticles are going to bind with your host system?
Okay, so basically, firstly you have to have a pristine material, yeah, and then when I show you some kind of the flowchart which I proposed, the silver nanoparticles were deposited within the method which was proposed, and the silver source was silver nitrate. So within the process, whole process, we know that we were able to deposit the silver particles on the surface of the material.
Okay, so maybe it's your silver nanoparticle is not going into the matrix, your host matrix. It's making a binary phase, because I could see some halo in the XRD peaks and also in the TEMI method. So, okay, maybe we can discuss later on.
Of course.
Yes, I think it's a good idea to switch to another presentation, because really we have to start another. So you can ask during the lunch break. Sorry. So thanks, Monica, again. Thank you very much. Okay, so the next speaker is Dr. Siti Salva Binti alias from Malaysia. The talk will be given about the chitosan polymers electrolytes, pioneering sustainable polymer electrolyte for electrochemical technologies. And Dr. Siti Salva Binti alias is a dedicated researcher and senior lecturer in the Department of Physics at the Faculty of Science, University Technology Malaysia, Johor Bahru, where she has served since 2019. With over a decade of research experience in applied science and technology, she is also a member of the OMRG research group and an associate fellow at CSE Nano UTM. Dr. alias specializes in materials for advanced energy solutions, including batteries, solar cells, and photo to hydrogen conversions. Her expertise extends to experimental design and materials characterization for photoelectrochemical cells and proton batteries. Additionally, she has contributed significantly to wastewater treatment research and has a strong focus on publishing high-quality scientific articles. With her solid academic background, including Master of Science and PhD in Materials Engineering from University of Science Malaysia, Dr. alias continues to make impactful contributions to the field of materials science and its applications in sustainable technologies. So, please, the floor is yours. Which microphone do you prefer? This one? Okay. So here's for switching and pointer. Okay, so please, the floor is yours.
Right, Assalamualaikum, and a very good afternoon to everyone. So thank you, Sharda, for inviting me to give this opportunity, right, in front of members from different countries. So for today, I would like to share on the chitosan polymer electrolytes, pioneering sustainable polymer electrolyte for electrochemical devices technologies. So as we know, this kind of polymer electrolyte has been used for almost 20 years, right? Starting from around 2000, until now it still be used as one type of the polymer electrolyte. And not only that, this kind of material also has been used to modify the anode or cathode materials depending on its purpose. And in fact, based on my own studies,
I also use this kind of materials for different kind application. Right. So we move to the contents of my presentation today. So I would like to share the current issue on this kind of materials and trends, and also why we choose chitosan, and also some of the studies that have been conducted in our lab, right? So what the current issue? And as we know, this kind of materials, since it is biodegradable based on animals in the sea, such as crabs, such as prawn, and so on, so it has a low conductivity, right? But I believe that most of us have been modified this kind of materials to make it usable, particularly for polymer electrolyte. And not only that, we use this kind of materials for lots of application. And also, this material kind of the polymer electrolyte based on biodegradable have another problem, such as mechanical stability, electrochemical stability, moisture sensitivity, and also complex fabrication process. So due to this, as we can see, most of us has been conduct this kind of research to cater this kind of problem. As we can see from lots of publication, okay? So the first thing first that we would like to share with other researchers is on the conductivity first. And then we move to the mechanical stability and other kind of material characterization, including the structural properties and also the morphology. So as we can see, this kind of material as ongoing research focuses on modifying this polymer structure, developing composite and optimizing fabrication methods to enhance its performance and its stability. So how about the trend and application of this polymer electrolyte application? So what we can see from here, there are various types of modification for electrochemical devices components, okay, and also the characteristic of good electrochemical devices. What we can see from the left side and the right side of this figure. So, as example, the various type of modifications, such as introducing a network structure, improving the contrast area, improving the thermal stability, and adding some kind of other polymer together with the chitosan. And as we know, our main target is we want to produce a good characteristic of our polymer electrolyte from the biodegradable material, and also to have a good characteristic. So what my lab, my team has been conduct the studies, although we are focusing on the fundamental studies, particularly in characterization of the material itself, but at least we show an improvement in terms of the performance, as I will present later. Right. So this is the energy storage devices that have been utilized, the chitosan-based polymer electrolyte. And not only that, we also use another kinds of biodegradable materials, such as cellulose, lignin, and other related materials. And of course, our main studies is focusing on improving the performance of electrochemical devices. As I mentioned just now, although we still on the stage of the fundamental studies focusing on the material characterization, but at least we show the improvement of the performance. And although it just maybe 5 to 10%, but it can be seen that this kind of materials have the good future outlook for various kind of electrochemical application. So this is some kind of the application utilize the polymer-based electrolytes. Okay. All right. So for the polymer electrolyte itself, so this is common types of polymer electrolyte. As we know, some of us use the polymer electrolyte, inorganic solid polymer electrolyte, organic aqueous electrolyte, and of course ionic liquid electrolyte, depending on our target application. And as we can see from this table, so normally the conductivity has various values in a range around 10 to the power negative 5 to then 10 to the negative of 1. But basically our target on modification of polymer electrolyte, we want to reach the highest conductivity up to 10 to the power negative 1. Okay, so this is the advantage and also the disadvantage of using polymer electrolytes. Okay, so although it shows the disadvantage, but we believe that by utilizing this kind of polymer electrolytes still have major advantage. And as we can see from the figures on the right side, the classification of materials used for making membranes, we believe that this kind of polymer electrolyte not just working for the batteries only, but it can be also used to another types of application, such as a membrane for the water treatment. In fact, as we can look at this kind of material, it not just work as a polymer electrolyte, but it also can be used as a separator for the batteries. So basically, it has a dual application as a polymer electrolyte and also as separator for the batteries if we utilize the ionic liquid as an electrolyte for our electrochemical devices. So, what and why we choose chitosan in our studies? As we can see from all the figures, it has lots of advantage by using the chitosan itself. And not only that, it starts with the chitin, right? And then from the deacetylation process, we can have the chitosan and it's ready in the powder form to be modified or to just mix with just a salt or another kind of materials for our desired electrochemical devices application. And what we can see in the next slide is example of polymer electrolyte based on chitosan for the vanadium redox flow batteries and how it can improve the performance of the batteries. And what we can see from the upper figure, okay, the separation of the favorable, unfavorable properties for the membrane, and also the chitosan-based membrane preventing vanadium ion crossover. So this kind of the characteristic is very important to improve the properties of membrane itself. Okay, so by improving this characterization, we not only improving the chitosan polymer electrolyte itself, but also the performance of our desired electrochemical properties. What we can see from here, as I mentioned in the beginning of this presentation, so this is the analysis, okay, what we have conduct to look what the future for the chitosan-based polymer electrolyte. And what we can see from here, the number of the studies is still outgoing. But what we can see in 2004, quite low. However, this data is recorded in early 2024. But when we read different kind of research paper, we can see that the trend is still increasing. Only the application is not only focusing on electrochemical devices, but lots of other types of potential application. Okay, so what are the characteristics and properties of the chitosan? So normally, since we are focusing on improving the polymer electrolyte itself, what we can see from here, the main thing that we want to characterize is ionic conductivity. And then also another types of properties related with our desired application, such as stability and also other related studies. And when we talk about the ionic conductivity, and particularly for the proton batteries application, of course, there are two kinds of mechanism, such as vehicular mechanism and also Grott's mechanism. As we can see, so for 20 decades, this kind of theory is not just in theory based, it's not just been based on our speculation. But by my presentation today, I will show all of you the improvement or the validation studies on proposing how H plus have been related, okay, with the chitosan itself, how the bond was interact between H plus and also the chitosan. All right, so this is just shows you the previous studies. Okay, what we can see from here that the electrolytes are grouped in progressive order of conductivity as follows. Here, what we can see from here, sulfuric acid has the highest one compared to the other types of the salt and also acidic. Okay, why this kind of situation occurs? So this is due to the ionic size governs the conductivity and how it behaves in the solution. So based on this, what we can see from this slide is the exchange between the dielectric constant, ionic conductivity, and viscosity is a part of the important result, okay, that we are focusing to improve our performance for the polymer electrolyte itself. Okay, so this is an example from the previous studies. By using chitosan polymer electrolyte for various types of application. And what we can see from the types of electrode itself, most of the batteries using zinc sulfate as a anode. Okay. Meanwhile, they choose manganese oxide as a cathode, right? And normally the performance is around 1.5 to 2.0 voltage. So I would like to share the work from our lab, the porous chitosan membrane in the proton battery. So basically, we have fabricated this kind of batteries, okay, by using zinc and manganese as anode and also as a cathode, utilizing a chitosan-based polymer electrolyte due to its low cost, eco-friendly, high hydrophilicity, and also good for proton conducting. Okay, so what we can see of the current problem, we use the solid polymer electrolyte, okay? So the dense surface and limited compensation with the salt. Compared with the porous chitosan membrane, it occurs, what we can see from here, the existence of the pores, okay? When we soak it in liquid electrolyte, it can enhance its application, particularly for the proton batteries. So, what the possible solution? Okay, so we offer three main objectives in our studies. First one, we want to prepare and characterize the membrane itself, to improve its conductivity and also to fabricate and characterize the electrochemical cell itself, right? So what the mechanism during desyndication? So in this study, we choose silica as a porogen removal, right? So we mix the chitosan and the silica first, and then we remove it. So what we can see, after a different amount of silica dispersed and diluted in chitosan acetate, so we can see that the removal of the silica has been occurred, right? By using sodium hydroxide solution. So we soak it at a certain amount of time, and then we can see this is types of membrane we can get from this kind of process, okay? So the sonication mixed with the porogen removal technique can improve the chitosan polymer electrolyte or membrane itself. So what the data that we obtain based on these studies? The first thing we characterize is its morphology, since we claim it has a porous film, okay, a porous membrane. So we choose FISEM, right, to look at the cross section. And we can see that the largest uniform pore obtained in a sample with a 2.0 silica, okay? So beyond that, we can see that the pores start to agglomerate. And compared to the sample with the lowest amount of the silica, so the pore is not uniform. All right, that's why we choose chitosan acetate with the weight ratio 2.0 silica is the best compared to the other sample. All right, so this is the relation between the water uptake, okay, for the chitosan acetate porous membrane, all right, versus the pore size. What we can see from here, the highest pore size obtained in the sample with the 2.0 silica. Then the ability of the waters fill up the membrane pores highly depends on the average of the pore size. Okay. After that, we further with the structural properties. Okay, the structural properties is very important to get the amorphosity of the membrane itself. So what we can see from here that after 2.0 silica, okay, there's a large of amount SiO2 trapped inside the membrane, and it shows not suitable for the polymer electrolyte application. Okay, next we choose ammonium acetate as an ionic liquid, right, to soak with that particular porous membrane. Okay, so the main thing why we choose chitosan acetate compared to other types of ionic liquid electrolyte because of, based on our previous studies in the lab, it shows it has the highest conductivity, okay, compared to other types of salt, right? Okay, so another performance is the temperature dependence, right, to get the activation energy, okay. So we can see that after soaking for 48 hours in ammonium acetate liquid electrolyte, it has the highest conductivity, okay, shows at the high temperature. And this is the purpose mechanism, right? So after this, I will show with all of you the validation that we has been conducted by using the computational studies. Okay, so this is the LSV result. What we can see from here, the sample with 20.0 silica, okay, and then soaking in liquid electrolyte ammonium acetate for 48 hours still has the highest breakdown voltage compared to the other sample. So we move to the thermal properties. Okay, why we choose this kind of analysis? Because we want to know either our polymer electrolyte, is it suitable to work at high temperature or not. Okay, so what we can see from here, right? So the porous membrane degrading depends on the duration of soaking. Okay. And then we move to the mechanical testing. So by using this kind of approach, we can see that the CA 2.0 silica has the second higher of the tensile strength compared to the other sample. And of course, the sample with the silica has the highest tensile properties compared to the other one. Why? Because after we soaking it in the electrolyte, of course, the tensile quite lower compared to the sample before we soak in the electrolyte itself. And then we move to the proton batteries discharge profile. Okay, what we can see from here that when the discharge occurs at 0.1 milliampere, it shows the highest specific discharge capacity is lower. All right, compare with the discharge current at highest one 5.0 milliampere. Okay, why this occur? This is due to the large pore size, high conductivity, high electrolyte uptake, and optimal background voltage increase. The discharge capacities is around 30%. Okay. Not only that, we also compare the performance of this kind of the batteries with the simulation by using multi-sim, right? Although the simulation one shows the lowest compare the real one, but it shows the possibilities to use the simulation approach to compare with the real application of this kind of proton batteries. So this is the output that we get from our studies. Okay, we cover the properties of the porous chitosan membrane, and then after that we soaking in ammonium acetate, and also we also characterize the properties of the proton batteries performance itself. So based on our studies, we shows that the potential of using chitosan-based polymer electrolyte, or we call as a chitosan membrane, for this type of batteries application, okay, the coin cell proton batteries application. So how about the validation via the computational studies? Is it what we said in the theory right or not? Or the computational get the different answer? So the first thing first, we use the molecular dynamic, okay? So it involves the computational simulation, right? Where atom interact under the defined physical law, okay? And we know that this kind of approach is widely used in material science, biochemistry, and also nanotechnology to predict molecular behavior. So this is advantage and the disadvantage by using the molecular dynamic, all right? So either looking for the disadvantage, of course, we are focusing on the advantage of using this kind of approach because it can handle large system effectively, capture time, depend properties, and also computationally efficient for large-scale system. All right, so the reason why we choose molecular dynamic because it is a semi-empirical and also DFT and AB initio method are the greater for electronic properties, okay? And why MD? Because it can capture ionic transport, miscibility, dynamically scalable, and also balance computational cost and accuracy. So in polymeric, okay, and also the ionic system, So we are divided into 4 types of the main thing, right? So the polymer blending, particularly chitosan in these studies, the ionic conductivity simulation, the structural analysis, and also the time-dependent diffusion. So why we choose this validation of studies? Because of what we can see the trend nowadays. So most of the research choose the computational methods to validate their data, okay? Compare we just run some kind of testing in the lab, okay? And then for the methodology, so it divided into the simulation, the force field, the system construction, simulation methods, MSD analysis, and also simulation goal, right, to evaluate the ionic conductivity of chitosan soaked in the ammonium acetate electrolyte. So what we can see from here that, okay, optimized structure of chitosan, ammonium acetate, and intermolecular interaction analysis beside its ionic conductivity analysis. What we can see from here, okay, so the chitosan with soaking in 5.0 ammonium acetate shows the optimum properties compared to the other concentration of the liquid electrolyte. Okay, so it shows it's in line with what we get from the lab. And in fact, for the effect of ammonium acetate electrolyte concentration towards the stability of the complex, we can see the trend based on the total energy and also the bond energy and also the angle energy, as we can see from both figures. Okay, so this trend indicates stronger interaction between the molecules as the concentration of the ammonium acetate increase. And then this type of interaction occurs, including hydrogen bonding, hydrogen intermolecular binding, and also intramolecular binding. And other characterization by using radial distribution function. Of course, it shows that chitosan soaked in the 5.0 ammonium acetate still show the highest conductivity due to the bonding reaction. Okay, this is the ionic conductivity analysis. And then again, by end of this computational study, what we can see that the interaction analysis, the energy optimization, RDF, and also diffusion of ionic conductivity prove our studies by using an experimental approach. Okay, so what we can summary based on these studies, the energy density enhancement functionalized on the strategies, conductive and structure optimization, and other types of approach is very important to show that the chitosan-based polymer electrolyte suitable for the various type of electrochemical energy devices. That's all. Thank you.
Thank you very much. There is time for one short question. Okay.
So thank you for the talk. So maybe I have mistaken, but in your experimental part, you have shown that your protons are exhibiting the conductivity by the hopping process. But your simulation model and other theory, you also included the diffusion, including the Einstein diffusion equation. So this conductivity is coming due to diffusion process or hopping process, or maybe it's a mixed form of the diffusion charge transport and hopping charge transport. And the second, the conductivity which you saw, the conductivity is increased. So is it increased due to the increase in the carrier concentration or the mobility increment of the ionic parts?
Right, thank you for your question. So for the first part, okay, we believe that the major contribute for the conductivity is due to the ion hopping and also mixed with what you said just now, right? So it's on the transportation, okay, the ion hopping, and then other types of kind of mechanism is also include. Okay, why I choose this the second one, right? Because from our lab testing, we get the ionic conductivity. But from what we shows from the computational, including the diffusion side, that's why we believe that it mix with the ionic ion hopping, and also the diffusion. All right. So for the second question, I think it's also contributed by the charge transportation also. Okay, so because when we choose H plus as our main contributor for the ionic conductivity, it not only just because H plus itself, but also other types of mechanism that include and also that contribute for the high ionic conductivity. And basically what we can conclude here is it mixed with different types of the mechanism, and also this mechanism can improve the conduction itself. Okay, thank you.
Okay, let's thank the speaker again, and we are closing this session. Thank you very much, everyone, and we are welcome for the lunch, I hope.
Thank you so much, sir. So first of all, I would like to thank Professor Karol sir for session chair. And I would like to request Professor Neelam Srivastava ma'am to come on dais to give a memento of our speakers. So first memento is from our session chair, Professor Karol sir. Please come on. And next one, our plenary speaker, Dr. Monica Mishalika. Ma'am, please come on dais. I would also request our invited speaker, Dr. Siti Salva ma'am, to come on dais. Dr. Siti Salva.
बस इतने ही है नहीं लास्ट टाइम ये मोनिका ये मारिया प्लानरी प्रोफेसर
Thank you so much, ma'am. Okay. एक उनका तो मिल गया ना, उनका
हो गया ना देने लेने वाला या और किसी का छोड़ दो और कौन चलिए वो हम करवा देंगे so I think before lunch session you at least believe that we have successfully completed this one session and now I requested all of you to gather in you can say first floor where lunch is ready and we all are invited you for lunch. But pray check one time this coupon is with you or not. Otherwise there are so many guards there. Okay? If not, then contact to me. Okay? Please proceed to floor 1.